This is 2.7, all about parent functions and transformations. Follow along with me on page 14 of your guided notes packets if you're in my Honors Algebra 2 class. We're going to be able to identify and use parent functions, and then we will also be able to describe transformations of functions. So this concept that I really want to drive home is the concept of parent functions. Okay, and so it's the simplest function graph in a family of graphs before it is transformed. Okay. And so what this means is it's the most basic form of a graph. So for example, if you think about linear functions, that's the one that we're typically the most comfortable with. Linear functions, y equals x is the most basic function in that function family. Okay, if we think about the linear family, maybe we have a crazy cousin like y equals x plus 1. A wild ant, y equals negative 1/2 x plus 4. There's all sorts of ways that we can dress up our linear function family, but at the end of the day, their graphs are still going to look like lines. Okay, and y equals x is the parent of that function family. A constant function, those are going to be our horizontal lines where y equals a constant number. And an absolute value function, the most basic form of the absolute value function family is y equals the absolute value of x. And then our quadratic functions, we haven't talked about these yet in this class, but we will be building up to that point. Y equals x squared, it's a parabola, and so it's a nice curve that looks kind of like a U. That is the parent function of the quadratic function family. So anytime we talk parent functions, we can talk about these crazy relatives as well. And so as soon as we start to add or subtract numbers or multiply out front by numbers, things are going to get a bit crazy with our graphs. Okay, and that's what this lesson is all about. So keep an eye on these parent functions. Okay, so big picture, what happens if we start to mess around with these graphs? Okay, so in Desmos, this is our parent function for the constant function, y equals 1. And I can play around with this graph. I can change the value of this constant. And what's going to happen to it? It's going to move up and down along the y-axis. Okay, so this table that I have created, it really drives home this idea that functions are machines that take points to other points. So when our function is y equals 1, no matter what we plug in as our input, the output is going to be 1. And that leads to this horizontal line that we see here. Okay, so this table is going to stay the same, but notice what happens if I slide up my constant value. My line starts to move up and down along that axis. Okay, until we reach back at our parent function. And then think about with our linear function, our most basic form is y equals x. Let's say I put a number, any number, in front of that x. I'm going to start to adjust the slope, meaning my line is going to start tilting. And let's say that I add another slider out here. Maybe I'm going to add a number outside of the x. If I start moving that, then I'm going to start sliding up and down this axis. So this idea of moving functions along axes is where we get this idea of function transformations. So notice my absolute value function, as I start adjusting the number in front of x, then my graph gets skinnier or fatter. And then when it's a negative, it crosses down, so I have an upside down V instead of a right side up V. And then when I start changing the number b that's added out here, we're shifting up and down that axis. So what would happen if I'm subtracting a number? It means I'm going to be moving down, okay? So there's all sorts of things that we can do with these function transformations. Okay, parabola, same idea. If I add a number and multiply it out front, it changes how skinny or fat my parabola is until I reach back the parent function here. Okay, so keep that in mind as we're going through all of these notation pieces, because I don't want you to get so lost that we forget what we're actually doing. So a translation moves a figure up, down, left, or right. Think back to geometry. If you're translating like a square in the coordinate plane, just means that you're sliding it. So you're sliding it up, down, left, or right. And so the same thing in a function. We can move all these functions up, down, left, right along the x and y axes. And so what that looks like notation-wise, this is where we're going to start to get lost. Okay, but keep in mind that we're just moving things around in the plane. If I have a number that is being added or subtracted outside of my parent function, that means we're going to move up or down. Okay, so think about if I want to play with my quadratic graph, if I'm going to add a number out here, I'm going to add a number out here. If that number is 0, I'm at my parent function. If I increase that number to a positive number, notice my parabola is just moving up the axis. If I move it down to a negative number, it means we're moving down. Okay, so that's all it means when we're adding a number outside the parent function, we're moving up and down. When we are adding a number inside the x part, so inside the parent function, the graph is going to move left or right. Something to keep in mind here is that the intuition is opposite. So when we're adding a number inside, our graph is shifting to the left, even though that's the direction of the negative x-axis. Our intuition tells us that we want to move it the other way, but it's opposite. So with the horizontal shifts, you have to reverse your intuition. A reflection is going to flip a line over the x-axis or the y-axis. So if we have a negative out front of the parent function, we're flipping over the x-axis. If we have a negative inside, then we may reflect over the y-axis. If the function is symmetric to begin with, we're not going to notice this reflection over the y-axis. If you think about the absolute value function, if I plug in the absolute value of negative x, because of the nature of the absolute value function, it's going to make it still look as if it's positive, so we're not going to notice this reflection over the y-axis. Dilations, we can multiply by numbers and get vertical stretches and vertical compressions. So this is the idea that I was playing around with a lot, let's see, with this absolute value function. So I'm going to delete these sliders for a second. If I'm just multiplying a number outside the parent function like this is where I get that idea of being skinnier or fatter. So if it's a fraction, so notice how at 0.2, which is 2/10 or 1/5, our V is really wide, really fat. Okay, so I would recommend just open up Desmos, play around with these sliders, and see what you can come up with. This idea of a vertical stretch or compression. Picture if you're like, so when my function is really skinny like this, it's almost as if I'm pushing on my horizontal axes. I'm pushing inward, and I'm pulling on my y-axis. Do you see that? See how it's like if I were to start tugging on this end and this end of my y-axis, then my parent function would get skinnier. Okay, so that's kind of what is happening with these vertical stretches and compressions. Horizontal compressions are similar intuition, except we're pushing or pulling on the x-axis.